In this video, we're going to see how we can use an autoencoder neural network to predict anomalies in a time series dataset. So this is a dataset that has certain values for some features in some time intervals, and in some of these time intervals, no anomaly happened, and in some of them, some anomaly happened. So we want to detect in which case, at what time and for which features this anomaly happened. And this will help us detect whether an anomaly has happened if the same features or similar features occur. And this is especially useful in ambient assisted living since, for example, one important task of ambient assisted living is fall detection, which is a type of anomaly detection. So in most cases, there will be no fall that we need to detect, but in some cases, a fall has happened, and we want to have a neural network that can learn in which cases or for which sensor values a fall has happened. So here we're going to use a time series dataset where we have when we have one feature, so that could be, for example, the value of one sensor, which tells us which has a certain value, and in some cases we have jumps in this value, so this value is much higher or much lower than usual. So first we're going to read in the libraries that we're going to use. So we're going to use NumPy, that we generally use as a helper for working with arrays, and pandas, which we use as a helper for working with tabular data, which we're going to use here. And then we want to import TensorFlow, and so we're going to import layers like this to work with them more easily, and we're going to also import matplotlib for visualization. Right. Next, we want to read in the data. So in this case, we have two data sets, one that doesn't have any anomalies and one that does. So we're going to read in both separately. So we're just going to use pandas like we did before. And here we also want to parse the timestamps, so we use parse dates true, and we set the timestamp to be our index column. And we do the same thing for the dataset with the anomalies. Right now, let's look at these datasets. So here we see we have this feature which has some values, and we have this timestamp, which we see we have one value for the feature every 5 minutes, and we encompass a total of 14 days. Let's take a look at the other dataset. So the one with the anomalies. So with the data we see here, we don't see much of a difference. So again, the values are generally in the same area, in the same bounds. However, we'll also will visualize this data set so that we can see where the difference is. So we're going to use Matplotlib for this. So let's see what the data looks like when it doesn't have anomalies. Right, we want to plot it. So we see here we have the data is generally in bounds between 0 and about 90. We don't have any big jumps, so it's low here, then goes up, then goes back down, but there are no jumps. So every time we have something that's in certain bounds. Now let's do the same thing for the dataset with the anomalies. So I want to plot the dataset with the anomalies. And here we see that we have this big jump right here. So we have the data is generally in bounds between 0 and 90, but there is this big jump here that goes up to 160. This is why we say we have an anomaly in this data set, and we want to be able to detect cases like this one. The next thing we want to do is pre-process the data. So first we said we're going to build an autoencoder network here, and we're going to use it to replicate the data. So we want to build a network that will approximate the data that we have, and then use that to detect the anomalies. But the first thing that we need to do is pre-process the data. So as we can see here, this feature has some values that are greater than 1. So we have some 18, some 21, some 20, and so on. Whereas we can see here on the graph, we have values between somewhere around 20 to somewhere around 90. What we want to have is we want to normalize the data so that we want it to have values between -1 and 1, because otherwise the neural network won't be very stable. So we're going to do that now. So we're going to compute the training mean and standard deviation. We're going to use the dataset with no anomalies because that's the one that we want to reproduce with the neural network. So we're going to compute the mean and standard deviation. And then we're going to compute our normalized data. And this we're going to do it just by subtracting so from each value that we have, we're going to subtract the training mean, and we're going to divide by the training standard deviation. So we want to divide this by the standard deviation. Let's sorry, the typo here. Let's see what this is gonna look like. So we can see now our values are much lower. So we have just all of these values that we have here, some minus or close to -1. And the values here would be close to 1, for example. Right, so the next step that we want to take is to group the data into sequences. We do this because, of course, we're going to work with sequences in the network, so we want to group the data into sequences the size of each sequence will be equal to the number of time steps that we have each day. And as we saw here, we have so we have data every 5 minutes. So we have 288 time steps per day. Now we're going to create sequences, so each sequence is gonna have 288 values in it. And each sequence is gonna have, so we're gonna take the values from this value until the 288th value, then we start from this value and we go until the 289th value and so on. So we're going to create a function for this. So it's going to take the values that we want to group and the number of time steps. So we're going to keep the output here. So we want to go through the length of the values, but we have to subtract the number of time steps +1, so we just don't want to go out of bounds of our data. So we take the value starting from I and going to I plus time steps. Right, and now we want to return this once we're done. And now this is gonna be our final training data. So I want to call this function create sequences on our normalized data. And we said we have 288 time steps per day. Now let's see what this X train looks like. So we see we have this array here, so we start with this value, then in the next step we start with this value, we have 288, and then we go on and take more values. Right, so this is what our training data looks like. We can also take a look at the shape of our X, of our training X. Right, so we see we have 3,745 of these lists, and each of them has 288 elements in it. Now we can finally build a network. So this neural network is going to have a sequence of length 288, and we have one feature and we have one feature in this model. So we notice that we don't have a Y here, so we just have this X train, but we don't have a Y train. So this is an unsupervised learning problem. So we just have this one. So we just have this training set, but we don't have any labels. So we don't have predefined values for which we know that an anomaly has occurred. Right, let's build the network. So this is going to be a sequential model, and we're going to have this. Again, we're just going to define the layers here. Right, we have the input layer. So we define its shape. So we define that we have a sequence length. The sequence length, that's this thing here. And we're going to say how many features. That's x train shape of 2. That's this element here. So that's 2. We have 2 features. No, 1 feature. Sorry. That's the second element. It's the element with index 2, and we have 1 feature. Okay, so this is gonna be another encoder that's going to use convolutional layers. So we said that we use convolutional layers for image processing, but those are 2D or 3D convolutions. We can also have a 1D convolution that we can use on this type of data. So we're going to have a 1D convolutional layer, and within it we're going to define the number of filters in this layer. So that's going to be 32. Then we define the kernel size, or how large we want this kernel to be. So we define some of the features of this layer, and we set the activation function to be the rectified linear unit. Now we're going to have a dropout layer. So again, we want to randomly set some of the outputs to 0. We're going to set that to 0.2. So we want 20% to be set to 0. And then we define another convolutional layer. Again, it's going to be a 1D convolution, so one-dimensional convolution, since we're not working with images here. In this one, we're going to use 16 filters with a larger kernel. So our kernel size is going to be 7 here. And we're going to use the real activation function again. So this is going to be our encoder part, and now we want the decoder, which is going to have the same layers, but just in the opposite direction. So now we do another layer, again a 1D convolution, but we want to also make it transposed. And it's going to look the same as the previous layer. So we have 16 filters, kernel size going to be 7, and activation is going to be the rel function. So then we go to this layer, we have a dropout layer, so again at the same rate of 0.2. And then we do this layer but transposed, so we add a 1D convolution transpose. And we have again 32 filters. Set the kernel size to 7 here. Right, so the kernel size is 7 here as well. Right, so we have a kernel size of 7. Okay, and finally we're going to have the output. Again, 1D transpose convolution. Here we have one filter. Our kernel has size 7 again. Right, this is going to be our neural network. So we have one input layer, then we have these convolutional layers that are part of the encoder and then the decoder. And then we should compile the model. We're going to use the Atom optimizer here. And we'll set the learning rate to 0.001. And the loss that we're going to use here is this one. Right, let's right, this is wrong. Right, now we have this model, and let's look at the summary of it. So we have a sequential model. We can see how many inputs we have in each, or what the shape is of each layer, and how many parameters we have, and the number of trainable parameters. Now let's train this model. So now we're going to use xtrain both as the input and both as the so we usually pass the x here and then y here, but we're going to use xtrain twice in this case because we want to reconstruct the data set. The original data set will also be the target. So we're going to use 50 epochs here, a batch size of 128. And we're going to use a part of this set for validation. So we're going to set aside 0.01, so 10% of the dataset for validation. Right, and we're just going to set this callback here. So I want to set the option for early stopping. Based on the validation loss. Right, so if the validation loss doesn't improve after a while, we want to let's put this here, we want to stop early. Right, so we can see how the training happens here. So we can see the changes in loss and validation loss. You can see that we're getting improvement. Right, so now we're done training. So we finished training. Now let's see how well the network was trained. We're going to look at the mean absolute error as a measure to see how how well the neural network we just trained reconstructed the training set. So what we're going to do is we're going to look at this mean absolute error loss for the for this reconstruction. And the way that we're going to predict anomalies is that we're going to find this maximum value of this mean absolute error loss. And so this will tell us what's the worst our model has performed when trying to reconstruct the sample. This is going to be our threshold for anomaly detection. So if we try to reconstruct something and the reconstruction loss for the sample is greater than the threshold, then we can assume that the model sees a pattern that it's not familiar with, and that's why it makes such a large error, and we can assume that this is an anomaly. So we're not going to look at the implementation details here. We're just going to look at this visualization of the training loss. We just see how just what the error is for each sample. So what's the difference between the predicted values and the actual values. So we have this bin here. We see for the largest number of samples we had an error around this area here, 0.045 to 0.0475, and the maximum is around here, so 0.06. We see that if we print this threshold, so if we have an error that's above 0.06, then we can assume that we had an anomaly. So we can just see how well our network reconstructed the first sample. So we see that it does this pretty well. So while we have these things here, so these small variations that the network doesn't reconstruct, these big variations Here, when it goes up and down a lot, we see that the network reconstructed that part pretty well. And again, it evens out here in this small changes here. And now we're going to test this neural network to see how well we can use it to detect anomalies. We first have to normalize the test data as well. So this is going to be our test. Right, so we're not going to compute this again. We're just going to normalize the anomaly data by using the training mean and standard deviation. Right, and then we're going to create sequences. And then we're going to use this normalized data. And we're going to have 288 time steps. Right, so we do that, and now we can get the loss and see where we have, how many anomalies we have and where they are. So we compute this the same way as before. We run a prediction on, so we use model predict on our X test to see how well this network is going to reconstruct this test data set. Find the loss. Right, so we do that, and the anomalies are the places where this loss is greater than the threshold we defined earlier. Now let's see how many of the samples are anomalies. So we do that by looking at this. So we have around 408 anomalous samples. We can also plot them. We're not going to look at the details there, we're just going to look at it. It should work. Right, so we have most of the samples have very low mean absolute error, mean absolute errors. So the mean absolute error for the most of the samples is very low, and then for some small number of samples it is much higher. Next we want to see where this. So we know that we know which samples are anomalous, and we want to find the corresponding time steps. In order to do this, we're going to look at the data values, and each data value is going to appear in time steps a number of times. Actually each data point that we have is going to appear time steps number of times. We had 288 time steps, so each data point is going to appear 288 times. So if we know that, for example, if we had time steps was 3 and we had 10 training values, then our data could maybe look something like this here. So we have 0, 1, 2, then we have 1, 2, 3, then 2, 3, 4. So we see that the 2 appears 3 times, since we have 3 time steps in each of these sequences. So in this example, if we knew that, so if we had something like this and we know that these samples are anomalous, then we know that the data point 5 is an anomaly. It appears in 3 anomalous. It appears 3 times and all 3 of them are anomalous, so we can assume that the 5 is an anomaly. So we're going to find this anomalous data indices. So we have the number of time steps minus 1. Right, so that's data anomaly normalized. Again, the number of time steps plus 1. Right, so we go through so we go through each for all this right, so we find the anomalous data indices this way, and then we can plot this to see what it looks like. So we're going to plot this and overlay it over the original data to see what it looks like. So this is going to be our Alright, it's going to be our anomalous data, and we're going to find the anomalous data indices. In it, and we're going to plot it. Right. So this is going to be in a different color so we can see it. So now if we run this, we can see that this data point here that had so this jump here in values is marked in red, so that was detected as an anomaly by this neural network.